Hi, welcome to this presentation about my experience teaching software engineering at EPFL. The key takeaway you should take from this talk is that you should strongly enforce lightweight mechanisms. Now let's talk a little bit about the context of this class. So we had two major constraints. First, there's not that much time. The courses were allotted about 2/3 of one weekday and had hundreds of students. Specifically, there were 2 semesters, 1 course each, 4 credits each time out of 30, and about 150 students per course, with a total of about 1 full-time equivalent staff. So how do we take students who are computer science students at EPFL? They're not software engineering students. They have learned mostly theory. They have learned how to program mainly as a way to apply theoretical concepts and to see how those work in small controlled programs where a skeleton was given to them. So how do we take those students and make them build an actual software product, not just writing the code, but everything from requirements to maintenance? So I will talk in this talk about 4 main habits that we had to break in students. First, that they tend to work in very large chunks. Second, that they tend to equivocate when asked questions. Third, that they lack a big picture view. And fourth, of course, this is a talk in 2024, so I have to talk about AI. There is a lot more in the paper, which I encourage you to read. So first, chunks of work. One common problem that students have is their first reflex when learning about something is, okay, well, let me first go and read the entire documentation for everything I'm about to do, and then I will build one giant piece of code, and maybe I will write some tests, and maybe I will ask my friends to vaguely look at the code, and that's how you build software, right? To work against this habit, we made the courses super interactive to make students realize that they should not be spending a lot of time on one activity without thinking about the big picture. So first, the theory course had a kind of extreme form of interactive exercises where at any given lecture, there were at most 15 consecutive minutes of teaching, followed by 10 to 15 minutes of exercises, and then more teaching, and then more exercises, and so on. And so students really learned in a hands-on fashion, and it also forced the lecturer to make sure that any explanation for any subject was very concise because, well, you had 10 to 15 minutes to explain it. You could not go on a long explanation of one concept in an hour. And in the project course, there were frequent merges because what students want to do is they build the entire project and they merge it at the very end, and this does not work in a team, let alone in a context where your requirements might change. So it's really all about telling the students that they really have to merge their code frequently. They don't have to build a cathedral, they don't even have to build a house. Maybe this sprint they can build just a window. And if they don't manage to build the entire window, that's fine, as long as they have built the entire curtains, or maybe just the bar for the curtains and have merged that. Because it's much more important, of course, to have built one feature 100% than a lot of feature 50% each. Next, one habit we had to break is students tend to not be sure about themselves when they answer and think that maybe if they say, well, it depends, there are reasons to think yes, there are reasons to think no, then they will get the points on the exam because we will say, oh, well, okay, you used the right words there. But of course, in real life, that's not how this works. If you ask a colleague about their opinion on a problem, you don't want them to just say, maybe, maybe not. And so to help deal with this, the questions in the theory exam were about real-world situations. And specifically, we had first theory questions that were about a real-world situation, like a customer is telling you something, or a colleague asks you something, and students had to give a 1 or 2 sentence answer. This was explicitly told to them. And that makes it much more real-world. It prevents students from answering in long paragraphs that don't really make any sense, and it also makes this a lot easier to grade. So this is not just good for the students, it's also just good for making the class scalable. The third habit that we had to break is that students often lack a big picture view. Because if you want to build or maintain a cathedral, it's easy to hyper-focus on what paint you should use in that one tower, or whether the stones are really quite arranged very well, when in fact the other tower is on fire and you really should be dealing with that first. So in order to deal with this, the practical part of the exam in the theory course had, again, real-world expectations, and more importantly, we did not nitpick what students were doing. So we told them, here is a task with clear expected objectives, not in terms of low-level things like you should use a visitor pattern, but in high-level terms like your code should be maintainable and this component should not depend on that component, and so on. And then we used automated tests to grade the correctness and manual review to grade the design. But we did not nitpick about whether they build the thing exactly right, whether the spacing or the formatting or the variable names are perfect. It's just like a real-world pull request. You expect somebody to review your code saying, well, overall your formatting and naming and so on is fine. Or, you know, you really should like improve it. But not to tell you, here in this line, in that column, you have one extra space, because who has time for that anyway? So the grading was about the actual design that they proposed, and the overall, is the code looking good, okay, or pretty bad. This also makes exams much faster to grade, and it avoids the problem of having to remove a lot of points from an otherwise pretty good answer just because the student was in a rush and did not properly format it. Again, makes the course more scalable, improves the student experience, everybody's happy. Now finally, what about ChatGPT? What about AI? Is AI a magic wand that will help students answer any question and make all exams pointless forever? Well, in my experience, AI is more like very strong coffee. It's going to help students get stuff done faster, but it will not fundamentally make them incredible developers. So, common problems that AI has when trying to answer an exam is, well, first, itself has a lot of common misconceptions, right? Because ChatGPT has swallowed the entire internet and is feeding you back pieces of the internet bit by bit. So if you ask it about something that a lot of people get wrong on the internet, well, ChatGPT might also get it wrong, like especially around Scrum, for instance. Second, often when you ask AI for an answer, it will give you these very long, rambling answers that cover every possible thing, just like what some students do sometimes to grade Grub, because they hope that if they have named enough buzzwords, then you will say, well, okay, your answer contained that buzzword, so you get the point. But if your exam is well designed, then you say, well, no, we asked you to say 1 or 2 sentences, you gave us 3 paragraphs, you get 0 points, period. And finally, sometimes AI will hyper-focus on one point of the question, like for instance, oh, you're asking a question about this snippet of code. Well, let me give you a giant snippet of code as an answer because I saw that the first 3 words were related to this. When in fact, the answer was something about the design of the code and did not require writing any code at all. This is also something that students do sometimes. It's just that with AI, they can now do the wrong thing even faster. So if your exams are designed properly, that's not really a problem. For projects, well, it's all about code reviews, right? If you write code with ChatGPT and then your teammates find your code readable and can understand it, and you can answer questions about the code you wrote, great. That's it. You want to use AI, have fun. So in summary, it's all about strongly enforcing some lightweight mechanisms, merge often, have exercises inside the lectures and force students to really get used to doing small chunks of work at once, and so on. You have to work against bad student habits because, especially in the context of a computer science degree, not a software engineering one, they have quite a lot of habits from math classes, like always asking the TA when they're stuck, that don't translate to software engineering. And finally, good software engineering practices lead to good courses. This is great because it means we can, as educators, reuse what we already do in our engineering of software to get great classes. You can get the paper and the artifact by scanning this QR code, and of course the artifact has been evaluated and granted badges.